Alright, so today's lesson is a recap, and we are going to look into a few things that you're seeing on the screen. So, first of all, we will talk on the elemental notation that you can see over here. We've got a symbol, we've got two numbers, and one of them, which is the small one, is your atomic number, whereas the big number is your atomic mass. So, the atomic mass is basically the sum of neutrons plus protons, whereas the atomic number lets you know the total quantity of electrons or the total quantity of protons, right? Now, by looking at this elemental notation and the symbol and these two numbers in this elemental notation, we can find out the number of electrons, protons, and neutrons. So, by literally just looking at this small number, I can figure out, I now know that my electrons are going to be 6, whereas my protons are going to be 6, because this is going to get determined by this small number that you see over here, which is your atomic number, which ultimately lets you know about the total quantity of electrons or the total quantity of protons, right? Now, now the thing is, for this big number actually comes with two quantities. It's basically the sum of neutrons and protons. And while I'm interested in just finding out the neutrons, what I will do is I will subtract this big number by this small number in order to eliminate the total quantity of protons from this sum so that I can eventually get the number of neutrons only from this sum. So, in order to get the exact quantity of neutrons, I'll just subtract this big number by this small number in order to get the neutrons. So eventually, I've got all the three values now. Always remember, when you are solving for this elemental notation, these are the only basic steps that you need to keep inside your mind, right? Now, moving forward with the electronic configuration. Now, how am I going to make the electronic configuration for carbon? It is very simple. The thing is that always remember that in the first shell, so the first shell is called as your duplet, the second shell is called as your octet, and so on. The basic concept in like making such kind of electronic configurations is that you make them sequentially, chronologically, in a way that is shown over here. But what I will do is I'll make sure that I make this diagram again so that we can understand step by step what we have done over here, right? Now, I'll first make my nucleus just as shown in the diagram. So in nucleus, you can see that I've got my neutrons, I've got my protons, and then for my first shell. So always remember that your first shell is duplet, right? So in your first shell, always remember that the maximum number of electrons that can come are just 2 electrons, right? Now, in total, we have got 6 electrons. So if we are going to accommodate the electrons in the first orbit, we will be we will be only able to put 2 electrons only, not more than that, because of the fact that the maximum number of electrons that can come inside the first shell or the orbit are the maximum 2 number of electrons. Now, for our second shell, we will then make our second shell, and what we will do is we've got 6 electrons. So 2 electrons got accommodated in the first orbit, in the first shell, whereas 4 leftover electrons will get accommodated in the octet. So an octet, always remember, it always accommodates, it can accommodate maximum number of 8 electrons. So what we can do is we can simply put the leftover electrons over here. So this is how our electronic configuration for carbon has got completed, where you are trying to show the nucleus, you're also trying to show that how the electrons are arranged in the orbits. And this is how you can make a perfect electronic configuration by looking at the subatomic particles of carbon. I hope this was easy and we'll move forward with a lot of practice problems now. Now, as we move forward, you can see over here, sorry. Yes, so we can see that we have got hydrogen over here, right? So for finding out the hydrogen's subatomic particles, the rule is simple. Look at the small numbers. So over here, I've got the numbers, they are basically identical. So I'll just go on with the conventional concept of, supposing and assuming that I've got my uh, atomic number beneath the symbol. So this is how I'm subtracting the atomic mass by atomic number. And in this case, we have got no neutrons. All right. So for the nucleus, we will declare in the nucleus that we have got no neutrons, we have got one proton, and this is how I'm going to enclose my nucleus, and this is how I'm going to make my first shell. And in the first shell, I've got my electron, and this is going to get accommodated over here. So for my first shell, for my first orbit, it's duplet, so I'm accommodating one electron, and this is how the electronic configuration, the atomic structure for hydrogen is developed. Now moving with the second example of helium. So for helium, let's say if I have helium and we've got our elemental notation which is over here, I've made it twice. So now let's make sure that very quickly by looking at this elemental notation, I can figure out the small number which is 2 and the big number is 4. Always remember the small number is going to be your atomic number, whereas the big number is going to be your atomic mass, right? Now, the atomic number, I'll repeat this again, always lets you know the total quantity of protons and the total quantity of electrons. So we've got them, the total quantity of electrons and the total quantity of protons. Now, as for the total quantity of neutrons, we are just going to subtract, this 4 by this 2 in order to get the number of neutrons, right? Now we've got our neutrons. Now, I'll make the same nucleus first, in which I'll declare that I've got 2 neutrons, I've got 2 protons, and then I'll enclose the nucleus. And in the first orbit, in my first shell, which is duplet, I'm going to put 2 electrons. I'm going to accommodate these 2 electrons. And in this case, we had 2 electrons. So this is how we could only accommodate 2 electrons in this first shell, and this is how we have completed our second electronic configuration or atomic structure for helium. Now let's move forward with lithium. So for lithium, the same concept goes for lithium, and I'll quickly make sure that we calculate the number of neutrons, protons, and electrons. So by looking at the small number, we've got our electrons, we've got our protons. By subtracting the big number by the small number, we've got our neutrons. Now, the same process. We'll declare everything in the nucleus first. So we'll go sequentially, chronologically. Now, 3 protons, 4 neutrons. For my first shell, I'll be accommodating only 2 electrons, which can come in the first shell, which is duplet, right? Now, for my second shell, I'll be accommodating the leftover. So how many electrons were there in total? So we had 3 electrons. So 2 of them got accommodated in the first shell, whereas the one which was being left over was carried and was accommodated in the second orbit or the second shell that you see over here, right? So this is how this is the complete electronic configuration, the atomic structure for lithium. So I hope this is making sense, right? Now, let's move on to beryllium and let's quickly make sure that we solve for beryllium. So for beryllium, we have 9 and 4. So neutrons, protons, and electrons. Then again, the same theory, the same concepts are going to repeat again. By looking at the small number, we have identified the number of protons and the number of electrons, and then 9 minus 4, sorry, will give you 5. So this is because we need to find out the number of neutrons, and for that we need to subtract 9 from 4, the big number from the small number, in order to get the neutrons. Now, the same strategy. We will declare the neutrons and protons first in the nucleus, right? So we've got 5 neutrons, we've got 4 protons, and then in the first shell, we have got 2 electrons that we can accommodate, because the first shell is your duplet. And for the second shell, we can accommodate 8 electrons at maximum. But since we have got 4 electrons in total, so 2 electrons got accommodated in the first orbit or in the first shell, whereas the leftover 2 electrons got accommodated in the second orbit or shell, which is octet. And this is how this electronic configuration got completed, right? So now moving forward with our last practice example, which is boron. So for boron, let's very quickly solve for boron. By looking at the elemental notation, we now know that we have got 5 electrons, 5 protons. 11 minus 5 will give us 6 neutrons. And then again, by declaring in the nucleus, we now know we have got 6 neutrons, 5 protons, and this is how we are developing a nucleus first, and then we are accommodating the electrons in the orbits. Now, so by looking at the situation, we have got 2 electrons which will get accommodated in duplet first, and then in the octet we will accommodate the leftover electrons. So in total we had 5 electrons. 2 electrons got accommodated in duplet first, and then we have got these 3 leftover electrons which were accommodated in the second shell, which is your octet. And this is how the electronic configuration for boron, or the atomic structure or the electronic configuration for boron has got completed. So this is what I wanted you all to recap for this lesson. And there are a few more things which we can discuss further on, but I would like to end the lesson over here, and I would like you to focus on solving questions from, let's say, if you're trying to practice this, try to practice all of the like the calculation of subatomic particles from hydrogen till calcium. So calcium would look like this in the periodic table. So you've got a journey to cover from hydrogen till calcium. So just let me know about it in the comments if you're having any problems, and you can solve first 20 elements in order to practice how to find out the subatomic particles and how you can exactly make the electronic configurations. So these are the things which you can, do on your own, and you can come in contact with me if you're having any problems. Thank you so much. Take care, and I'll see you in the next video.